and so the energy is being released. But if it drops, it's going to be in there because the energy is being absorbed, so it's going to be cool.
Right, so the energy is being absorbed into the system. Does that mean the system is getting warmer? Yes or no? Be confident. It's a yes or it's a no. No, it does not. So that's the other point. It's later on in the free response. But if energy is being taken in, or energy is absorbed, that's the word we use. If energy is absorbed, you know that's endothermic, right? That's kind of a definition. That energy is being absorbed, but what is it doing? What's it doing for the reaction? It's helping the reaction, right? It's being used, like for example, one of the examples was breaking bonds. So this energy being absorbed is being used up. It's being used to force the reaction to occur, to break the bonds, to allow it to meet activation energy. It's doing something, and it's gone. Once it's used up, it's gone. It is used up. Or it's consumed is another way to say that. So it's no longer there. So can it make the temperature of that system go up if it's no longer there? No, it's not there anymore. It's not actually in the system. It's been used. So if it's endothermic, it's not going to increase in temperature. It's going to go down, or the surroundings are going to go down in temperature because the energy was put into the system. It's no longer in the surroundings. Give me a thumbs up if you wrapped your head around that a little bit more. I need to work on that with some of you guys some more. I think you'll have to wrap your head around it to correctly correct your corrections. Correctly correct your corrections. Okay. Okay, so B, definitely, if you saw the temperature drop, that means it got colder. If it got colder, it's endothermic. A lot of you guys said it was endothermic, and then you recorded your Q value as negative. No, you guys it really tries to guide your footsteps. It's like, okay, it's going down. Okay, it's endothermic. And then it asks for Q, and then you still put a negative value for Q. You have to self-correct. Your Q of the water versus Q of the dissolution process, those are referring to the same value, but one is negative, one is positive. The dissolution process was the positive value. The negative went along with that drop in temperature, that negative 3.2 degrees Celsius. So yeah, that was the negative value, but remember, the Q and Q's are equal to each other, but the system it was talking about was the solution process, which was the endothermic process. So that might help you on VI. Did you, what did you have to do with the masses on VI? Look at this with me and not your lap for a moment. Masses have to be summed here. So that would have been the mass of the water plus the mass of the solid salt, or the urea that was given to you. And that 4.2, some of you guys still use 4.18, but they specifically said use 4.2 because it was accounting for like the specific heat capacity of the urea as well. So you did have to use that C value they gave you. And then how would you find H of solution after you found Q? How do you get delta H from Q? Divide by mole. So there was 1 point awarded for mole calculation, 1 point awarded for setting up Q over mole to give you delta H. I didn't tell you guys all the points, I'm sorry. 1 point for the correct Q value of dissolution to be like positive 1300-ish. It was, you did have to look at your sig figs. That's positive 1300 joules. For part D, for the delta S of solution, this is a point that I need to make because I make a lot of assumptions about your math credibility, and some of you guys need a little bit more help with your math. If you have delta G is equal to delta H minus T delta S, and you want to solve for delta S, mathematically, tell me your first step to isolate delta S. Okay, I'm going to subtract delta H. You can do that, or you can add T delta S to the other side. But these two things, you can't just divide because these are related through subtraction, not division or multiplication. These are related through addition and subtraction. I subtracted delta H first. So I got delta G minus delta H is equal to, this cancels, right? Negative T delta S. So then how do I account for the T now? divide by negative t. And one of you guys said divide by negative t, then you forgot the negative. Okay? So in terms of this now, delta t cancels. So then up here you had like a negative 6.9 kilojoules per mole for your delta G value, minus your delta H they gave you at 14.0 kilojoules per mole, over negative 298, because that was your Kelvin value. What should the end value, end units of S be here? Either kilojoules per mole K or joules per mole K. I think they said to go to joules per mole K in that one. Yeah, they said go to joules per mole K, and then some of you guys even didn't give it correct units, so you got to the final answer with not correct units, you didn't get any credit, which is harsh, but it's for thermochemistry, it's all about the units. E was mostly fine if you made it that far. I did give you a credit despite the statistics not being correct. And then for F on that one, F was if the urea begins at a lower temperature, what's going to happen to the delta T? Because remember, this was going down, and remember that graph went down, right? Start the urea off. Now I put it in that water. That water was at whatever, 25 degrees C or whatever it was. If I put that urea in there, what's going to happen to the delta T? What's going to happen to the final temperature if I put cold urea in my water? It's going to be what? A lot lower. So we drop down to like, I don't have my graph in front of me, let's say 21 degrees Celsius. It's probably going to drop to like 18, 17, 16. It's going to drop lower. So the T final is going to be lower. But what's that going to do to delta T? It's going to be higher. Delta T will have a bigger magnitude because we're dropping from a decent temperature down to an even lower one. So delta T will be greater. So if delta T is greater, what happens to Q? Q gets greater because delta T and Q are directly related through MCAT, right? So if delta T is greater, then Q is greater. It's a greater. Q is greater. And then if Q is greater, this is an endothermic process. What happens to delta H? Guys, I need your help here. I don't want to review your test without you. I'd like to review it with you. It is also going to be greater. Because how are Q and delta H related? Directly, right? So delta H is equal to Q over moles. So if I increase Q, then I calculate delta H to be larger as well. Number one was a hard one to start on, but I thought it held your hand good to me throughout. But we got to work on that a little bit more. So I'm going to have another thermochem like quiz or something where I can help you average your test. I haven't figured that out yet, but I do need to test you again on this because I don't think you mastered it yet. 2, I'll briefly go over this. Most of you guys got 2A, which was the delta S. How did you calculate delta S in number 2? And so when you say products minus reactants, I had numerous people not put their coefficients. It's a summation of all the products and all the reactants, means those coefficients do apply. So the summation of S of products, I'll put a little n in front of that because you need to multiply your S value by your moles of products minus the summation of N of reactants. Sorry, reactants. S of reactants. So this first step takes about 3 seconds. When I do recap with thermochem, meaning retest you, re-quiz you to give you some help with your average, I'm going to ask and require that you write down your starting point, your substitutions, and then your final. Some of you guys went straight to substitutions and final. You did okay. Some of you guys got no credit for setup because there was literally a point for setup, and you didn't have a setup, so that couldn't even give you the point. And I'm trying to show you guys those rubrics because it gives you some indication. It's not me, it's the AP. It's kind of how it works. So even set up like that, I think, Alvin, you're probably one of the ones who did the some with just setting up. Some of you guys didn't get all your points for setup because of that. So this was 1 point for setup. Joules per mole K should have been the final unit for S there. It was like 127.2 for your final value with correct sigfigs. That was for A. For B, it gave you the bond enthalpy, yeah?
So you always need correct units to get points.
For thermochemistry, it is the one that's like super, super important. Everything else is important. Thermochem, because there are so many units, you have to have correct units. Because it'll say on the rubric, correct value with units. And if you don't have it, you don't even get a half point. They don't do half points. I graciously gave like 3 people half points because I was like, I can't give them no credit. So I was like 127.2 joules per mole K. Okay, so B, how did you get delta H of reaction? On B. Say it again. So the bond association, but how do you calculate that? Thank you. It's bonds broken. And bonds broken come from breaking reactant bonds minus bonds formed, which is forming product bonds. This was the one that was reversed. So you must first of all, you must count your bonds correctly. I still had a couple people not count all their bonds, and I did those structures so that you could like cancel them out as you went. I think Courtney's one that circled them all to make sure she counted for all of her bonds. It's just you need to find little tips and strategies that help you account for all the little tiny details that do exist. And at the end of this, your value, when you recalculate, because you will recalculate, you get 49 kilojoules per mole. Well, that's our delta H, right? What does that mean about my reaction? What does that mean about my reaction? I'm trying to help you guys, so you gotta help me. Say again? Okay, first off, it means it's endothermic, right? Okay, so endothermic, great. But it said take delta H and refer to how the temperature would change back to part B. Well, part B was regarding everything all about bonds, right? Bond association energy. So what does that value actually mean?
So more energy to break bonds.
More than to release when it forms, right?
Yeah.
So more energy to break bonds than energy released when bonds are formed. So I'm abbreviating here a little bit. So in that case, this more energy is going into the reaction than coming out of the reaction. How does that relate to temperature change? More energy is being sucked into the reaction and consumed and used up. The surroundings should get colder. And just like you know, you are now probably memorizing endothermic surroundings get cold, exothermic surroundings get hot. The thermometers will work the same way. They get colder or they get warmer, and in the same respect. So that's going to mean energy is being absorbed, so the temperature should go down because it's going to get colder because it's being all the energy is being consumed and used up. I'm going to keep repeating that. I'll do 3 later because I got some people who were just looking at lab stuff and not really paying attention. So let's jump to lab for me. I'll help you guys a little bit more with corrections later, but I at least want to give you some tidbits that there'll be a little bit more of this coming soon. You guys ready for lab stuff now? Switch modes for me. Switch modes. So I just want to briefly go over the pre-lab questions. A lot of you guys did a good job with that. I'm going to do some oral review. If you need to add some now, or add a comment so that your group can talk about it later. I'd rather you guys do it in a group setting than in an individual setting, because I think you get more out of it. That's my goals anyway. So in terms of the crystal violet, it already had that solution prep for you. I had your sodium hydroxide prep for you. You are not reacting yet. What's the very, very first thing you have to do, according to what it says here on part 1? You have to make a calibration curve of what? Of CV, right? So your very first thing is you're making 5 dilutions of CV. You're taking that 25 micromolar, and you're making 5, 10, 15, 20 micromolar concentrations, measuring the absorbance. Once you measure the absorbance, you have a calibration curve, and that's it. Have you used the sodium hydroxide yet? No, because does the sodium hydroxide, well, first of all, does the sodium hydroxide affect the absorbance? Savannah's like, sodium hydroxide is clear, right? So it shouldn't affect the absorbance. However, what's it doing with the CV? It's what? Right, it's reacting with it, consuming it. It's no longer purple, it's going clear. So you can't get an absorbance reading from a reaction that's in progress, because that's not for calibration curve. That's for like the legit kinetics part of this lab. That's the actual rates of reactions. Yeah.
When we're doing the calibration curve, we do need like a 0 molar one, right?
Because that's gonna be your y-intercept. Hopefully 0 concentration, 0 absorbance. That's our goal, right? Okay, so based on the absorption spectrum, I think you guys did okay with that. What was your approximate nanometers you would set your colorimeter at? 590, 585. Now, note to self, I have one spec 20 out. No one said spec 20. Most of you guys said device. And I was like, oh, right, well, that's specific. So I pulled out 5 colorimeters, one spec 20, which I don't have on yet, but I'll get there. I have another spec 20 in the back. You need to decide if you're using the graphing devices, meaning the Logger Pro system with the colorimeter, the little device that you stick the cuvette in, or the non-graphical device, which is the spec 20, which you have to input your own data into a graph. Make a decision when we get back there. So you guys will notice that when you do use a colorimeter, I think the closest setting is 565 nanometers. They only have 4 settings in the colorimeters, whereas the spec 20 has an unlimited amount of wavelengths. So note to self, 565, I believe, is the nanometer that you have to set on a colorimeter, which would cause some error. Okay, well, that's great. Okay. You know how to, most of you have to grade on your setting up your solutions, but I didn't see a lot of work on that. I just saw like prep the solution. Like with what? Are you using graduated pipettes or using graduated cylinders? So you should be writing down these notes for you. I'm giving you some oral feedback right now. I need a little bit more dilution equation or equipment on that one. Number 3, you guys did good on, do you expect the colorimeter's absorbance reading to change during the reaction? Yay or nay? Definitely, right? The absorbance is going to do what? Go down, because absorbance is reading what? So how much light is absorbed by a concentrated species that happens to be colorful? Well, if it's no longer there, it's going to be transmitting light, not absorbing light. So the transmittance is going to go up, the absorbance is going to go down, and you need to have some reasoning there because you know how the reaction, a little bit how the reaction works. Number 4, I'm going to have to do on the board. I'm going to do on this board. Yeah, I'll do on this board. So this is a reaction, right? And we know we can calculate concentrations of reactions. We can use a little stoichiometry if we need to. This is the part I'm pretty sure there was maybe one group that got somewhat close, and I had one group that said, through common sense, blah, 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 blah. And I was like, all right, common sense works. And in chemistry, no one gives you any credit for your common sense. People give you credit for data. So let's get that data. There we go. So the reaction is, and if you want to write this down really neat, you can just take a picture and stick it in there, and that might be better than trying to type this. So before the lab, it says a 1-to-1 ratio of sodium hydroxide to CD versus a 1,000-to-1 ratio of sodium hydroxide to CD. So if I have NaOH plus CD makes colorless, whatever, we don't really care what the product is necessarily. And I have a 1-to-1 ratio. And I'm telling you right now, this reaction, which you guys saw a little bit in the pre-lab reading, it was like a 1-to-1 made one of these products, whatever it was. So I'm just going to tell you it's a 1-to-1 mole ratio. If I have 1 mole of this before the reaction and 1 mole of this before the reaction, oops. What's happening during the reaction? What's happening during the reaction? You guys are smart. I'm not going to tell you. What's happening during the reaction? First off, what happens during every reaction? Reactants get consumed, products get produced, right? So what's going to happen to these reactants? They both get consumed because it's a 1-to-1 ratio. They both get consumed in equal amounts, right? They're both technically the LRs because they're equal amounts. So minus 1 molar, or 1 mole, minus 1 mole, 0, 0. How much do you have left at the end? 0. So some of you guys are like, oh, I'm going to have 50-50 left at the end. Not really. That's your initial concentration, so 50-50 because it's a 1-to-1 ratio. But you need to think about how they react. They react completely together to negate them all together. So that's not really helpful for our particular example in this lab. And in this lab, we're actually going to flood the system. We're putting a ton of sodium hydroxide in there. And we're putting like a couple drops, just very, very little of the CD because we're using a 25 micromolar solution. It's very, very dilute. So if I had a 1,000-to-1 mole ratio, 1,000-to-1 ratio of how these are consumed, if I have 1,000 moles of this and 1 mole of this, who's my limiting reagent? Certainly the CD, right? Like I've got 1 mole of that and I've got 1,000 moles of this other one. So what happens? You subtract the 1, right? You're going to have to get rid of the limiting reagent, which happens to be the CV in this case. And when you subtract that on both sides, you have 0 left of your CV. So should this have a color? After the reaction, it should be very clear, not purple. And after the reaction, you're still going to have 999 moles of this left over. So then it said to tell me the percent of sodium hydroxide left over. For the first one, it was 0% of sodium hydroxide left over because it was 100% consumed with the CV. And this one, how much is left over? 99.9% left over, right? So did we really put a dent in the sodium hydroxide on the second round here? No. So in essence, does the concentration of sodium hydroxide change over this particular example? Does the concentration of sodium hydroxide change? If 99.9% remains, heck no, 0.1% was used. The concentration is basically the same. So what we are doing is we are assuming, and sometimes assuming is no good, but we are assuming that the concentration of OH, concentration of hydroxide, initial approximates the concentration of hydroxide final. And when we do that, it makes our rate law so much more achievable. Okay. So if we can do this, if we can set up a system like this, that makes our rate law achievable. Are we setting up a system like this in our lab today? What's our relative concentrations between our two species? What's our relative concentrations? Maybe tell me the concentrations of our two species. 0.2 molar for the sodium hydroxide and 25 micromolar. Well, what is that in terms of molarity? Extreme. So 2.5 times 10 to the fifth molar. So we're comparing this, which is our CV concentration, to this. That's what, 6 times, 5 times more? No, 100, 1,000, 10,000 times greater, right? Something pretty dang significant. So we have an issue here. We have a very big difference in concentration. Is the hydroxide concentration going to change significantly over the course of this reaction? No, the CV is going to run out, right? It's totally the limiting reagent. It's going to run out like that. It's going to change from purple to clear. The hydroxide concentration is going to change a wee bit, but who cares because it's not significant. So that's going to be important when you find your rate law. Okay, so for the last part, you guys did your graph part. How are you going to do this pseudo rate law constant? So I explained this to one person earlier. Maybe they can help me. We shall see. What's our generic setup for our rate law? Not the integrated rate law, for our rate law for this particular reaction. Rate is equal to, there's something up here first, right? Concentration of CV. So K, concentration of CV. To the W power, okay? I'm just making up letters, and of OH. And I'm saying no sodium hydroxide, or no sodium, it's a spectator on, but you could put sodium hydroxide there. To the Y power. That's our rate law, right? Now, in your particular procedure, the procedure was almost 100% laid out for you. If you read the procedure section of this little lab, Investigation 11, it didn't give you values, but it gave you some good guidance. I can't really measure the rate of this reaction with the colorimeter, right? But what can I measure with the colorimeter? Absorbance, which is related to concentration. Okay, so I can measure the concentration, and I can measure the web. I can always measure the web. Time, thanks. Okay, I can always measure the time that the reaction takes place in. I can also do, so I can either compare concentration versus time, or I can manipulate the time with the change in concentration. I can find the rate. So I can do either the differential rate law, which is the very first type of rate law we did, or I can take concentration versus time, and I can do the integrated rate law, which is the second style of rate law we did. It's up to you which one. I prefer the integrated because I don't have to do any manipulation to get rate. I can just pop time in my graph, see which one's linear, and go. So in that case, I think most of you guys did choose concentration versus time. But then you guys were saying, what were you guys saying? Oh, you were saying do this 5 different times by mixing different parts sodium hydroxide with your CV. How many times really do you need to do this? Just once. But a good chemist will do it twice to get this exact same trial done twice so you can compare your data. So do not change your concentrations through 2 or 3 different times. Stick with your one concentration of CV. If you want to dilute it, by all means dilute it, but that's more work. Put in your sodium hydroxide and then let the reaction run. However, when you put this in there together, you guys know you're going to be putting this in cuvettes, right? Cuvettes are really little. You're going to have to, in about 2 nanoseconds, put some CV in there, put some sodium hydroxide in there, give it a little shake, pop the lid on, put it in there, collect. And it took me more time to say that than it should take me to do it. Because immediately upon contact, it's going to start reacting, right? What's going to happen to the color of your CV? It starts to go clear, right? So you got to be really fast with it whenever you do the reaction. Okay? All right, and then so the last point I'll leave you with is we cannot figure out this concentration. Why not? We can't figure out that concentration with the colorimeter. Why not? It's clear. I can't tell when it changes, right? So I need to find a way to ignore that, and we are going to try to ignore it because it's not changing, right? So the concentration of OH is not really changing. We're flooding the system with it. It's not changing over time, so it's not necessarily impacting the rate of reaction. So what we do is we can say, okay, this guy, I can't quite find either because I don't know this guy. So what you do is you set up a pseudo rate law, which is the pseudo rate law constant, that takes these two pieces together. Okay, we're going to make a new rate law constant which encompasses them both. So K prime or K star, I think it was how it's denoted, is equal to K, the initial rate law constant, times the hydroxide concentration, because we can't really find either of these initially. So if we plug this in into where these two things exist, we have a rate law that's achievable, which is rate star, I think is how it was denoted, is equal to K prime concentration of CV to the W power. Because if we can figure out this, we could always backtrack if we need to, but we could definitely figure out this because we can find the concentration of the CV. We can use the slope or whatnot to find our K, and we can find our rate. I hope I did not just confuse more of you. I hope I cleared up a couple things. But, do you have any questions before we go back? Yeah.
So how are you going to use that to find the order?
You may not use that particular law to find the orders. You can, like I said, I prefer the integrated because I can just plug time in and be done. I don't have to find my own rate. Do you guys know what you're doing? I feel like it's a little weak right now. I got no response to it. So go back to the labs. Let's get started. You have an hour. Grab your test if you didn't already. We went over the test for like 20 minutes, so the video's on. I'm expecting you are dividing and conquering here. Dividing and conquering. I also need to know what kind of present you need. I'm putting the equipment back here. You can come grab it if you need it. You're setting up Lava Pro. You need to make sure you extend your time so that you can actually successfully get what you need. The crystal violet's back here. The sodium hydroxide's back here. I want you to grab them pipettes over here. If you get crystal violet on anything, it will stain. So I see a lot of small white today. Don't stain yourself. So question 6 asks you to design an experiment, right? So where you can find both W and K. So, okay, so if you have to design an experiment to get data, the data that we were just talking about, you would get was what?
It was the rate and then the K with.
Well, the data. So rate's not really a point of data you can get. Because you have to calculate that yourself, right? Because rate is change over time. You have to calculate that. It's not a piece of data.
Yes.
But what is the data that goes into rate?
Wouldn't it be like, it's not when you dilute it.
Well, so that dilution is, if you're doing the very, 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 very beginning part, which is the calibration curve,
Yeah.
do you know how to do that?
Yeah.
Okay, scratch that, you know how to do that.
So this is like the kinetics part when you're making the reaction and then you put it into
Colorimeter, what's the colorimeter reading?
the absorption.
Which we will then convert to, so the first thing you write is going to read absorption. And that's not necessarily a data point, that can be plugged into rate law, but what does absorbance relate to?
Concentration.
Of CV, right?
Yes.
Okay, so basically you are achieving the concentration of CV. And you can collect the concentration of CV over every second, right? So you are, basically your lab is collecting concentration versus data.
Okay.
Which type of rate law is this? Integrated or the differential one that we did at the very beginning?
No. Would it be the integrated one?
Right, so what you'll do is you'll plug this data, into the 3 integrated rate laws.
The first order, the 0 order, and the second order.
And then see which one's most linear.
Gotcha.
That's it. So you can write that up a little bit better. Okay. And
I understand what you were saying.
I'm going to leave that right there for you, okay?
Okay.
So the very first thing you guys are likely doing is setting up all your dilution so someone can measure the absorbance back to back to back to back. You need to get your absorbances first because you can't do your rates just yet.
We don't have to.
Yeah, it was supposed to be like,
Yeah, that's what we're trying to figure out.
Guys, please don't hesitate if you have questions. I'm going to look at your procedures a little bit more in depth right now after I've gone over the lab a bit more.